Good afternoon, everyone. Thank you for joining us today in the 10th talk of STEM's Lecture Series 2021. Today we have Professor Meena Mahajan from IMSc with us. Let me give a brief introduction about her. She completed her PhD from Department of Computer Science, IIT Madras. She is currently the member of Board of Trustees as Paper Chair, Computational Complexity Foundation Incorporation. Her main interests are complexity theory and computational complexity. And today she will be talking about a very interesting topic of how can we know whether two people are connected just by asking yes or no questions. So before we start, just a couple of quick instructions. Please use the chat box for asking your questions. We will take up them at suitable times or even in the end. And please turn on your cameras if possible, and so that makes the session more interactive. And you can also ask questions directly to the professor at the suitable times. Hope you all enjoy the talk. Over to you, Professor.
Thank you, Amit and Anirudh, for inviting me to give this talk, and I'm very happy to be talking to this audience at the STEMS series. I hope you will find what I'm going to talk about interesting. It's not standard textbook material, so I hope that there will be something new in it for everybody here. Yeah. So some of you may have seen the abstract of this talk, but if not, my very first slide is basically the abstract of the talk. So here's the first slide. We are asking questions and trying to figure out connections. So there's this huge social group, and the social group, for instance, could perhaps be on Facebook or on Instagram or on something like that. And so especially if it's on something like Facebook, it's like thousands, millions, even more, those many people. There are some connections amongst them, and it's very difficult to say a priori whether everybody is connected to everybody else, or are there some disconnected social groups within them. So what you want to know is A somehow connected to B? There are these two people, A and B. Like maybe I am A, I am sitting here in Chennai, and B is some name which has popped up somehow in my horizon, some person sitting in Germany whom I don't know at all. Maybe I don't know at all, but it's possible that we know somebody who knows somebody. I know somebody who knows somebody who knows somebody who knows that person, and I want to know whether this is the case or whether it's really somebody completely unknown. So this is the question that we want to know. Figure out if A is a friend of B, or a friend of a friend of B, or a friend of a friend, through whatever kind of connection. Are A and B connected by a chain of friends? Now the catch is, this network, the social group, is huge. So you can't go, it's not as if you can just look at the picture of the network and figure out whether there is a connection or no. So you have to ask questions, and the kind of questions that maybe you're allowed to ask in this setting are, you pick two persons, say X and Y, and ask, are they friends of each other? And you will get an answer, yes or no. So you can choose what X to pick, what Y to pick. But once you pick X and Y, the only question you can ask is, are they friends? And you will get either a yes or a no answer. So now how will you proceed in trying to figure this out? A is fixed, B is fixed. I know who is A, maybe it's me myself. B is somebody else. I just know the login name of this person, B. And I want to figure out, is there a connection? So what is the first thing that you would ask? Anybody can pitch in and tell me what you feel.
Maybe we will look at the friends of A first, like who all are the friends of A, and then look at each of.
You're trying to figure out whether A knows B via some connection. The most obvious thing is to check whether there is a direct connection between them, right? So what is the first question that you would, almost certainly, what is the first question that you would ask? Is A a friend of B? Because that will completely take care of everything, right? So the first question would presumably be that. But then, so if the answer is yes, then you know. But if the answer is no, then there is a lot more that you would still need to, then you'll need to figure out about whom do I ask next. So let's try and look at some example. Here's a very small example. This is how I'm going to pictorially depict the network. Okay, there are these nodes. These gray color circles are the nodes. Each gray circle stands for one person on this group. Now I said that it's a huge group, but this is a small example. This has just 12 people in them, and in that, this one particular person represented at this node is A, and this person represented here is at B, and I want to know whether they are connected. So if this is A and this is B, then you can see here from this picture that they are connected, and in fact this edge here shows you that they are connected. So this line which connects them, the line connecting two circles tells you that the persons represented at these two circles are indeed friends. So if this is A and this is B, I hope you can see my cursor moving back and forth between, yeah. So if this is A and this is B, there is a line between them. That means they are friends. And if they are friends, then they are connected. Okay, but maybe A is something else. Maybe this person is A and this person is B. And now you want to know, are they connected? Well, there is no direct connection between them. Okay? But in this example, we can see that even with this choice of A and B, yes, they are connected. Here is a way in which they are connected. A is a friend of this person, who 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 is there's a kind of chain of connections which then tells you that indeed A and B are connected. In fact, this is not the only chain. There's another chain which goes like this, and then you go up here and come here and then go to B. So there are chains which tell you that yes, A and B, even though they don't know each other directly, they are connected to each other in some way. What if this is A and this is B? Are they connected to each other? Will you try to search for a connection and then it turns out that no, they are not connected? How do you know that they are not connected? Well, here now you can see that there are some colors which I have put on top of this network. Some of the nodes are colored pink and some are colored light blue. And notice that the pink nodes, there is not a single connection between a pink person and a blue person. Okay. But A is a pink person and B is a blue person. So not only is A not connected to B, but anybody else whom A is possibly connected to in this coloring, all the people whom A is connected to are also shown as pink. And all the people whom B is connected to are also shown as blue. And there is just no connection between a blue node and a pink node. So A and B are not connected. So in this little example, we could just kind of visually look at the way the edges are drawn, who is a friend of whom, and we could figure out, whether they are connected or whether they are not connected. So to make this a little bit more formal and precise before we proceed, let me clarify that this network that I talked about, this network of social groups, we are modeling it as a graph. Now, a graph is something that in discrete maths we see all the time, especially if you have already reached higher school, college. But if you are kind of just at the beginning of high school, maybe you think of a graph as a plot that you draw on a graph paper, X, Fx, you plot that. Those are also graphs, but what I'm talking about here is a different kind of graph. So when I say a graph here, what I mean is that there are these circles which are here are nodes. They are called nodes or they're called vertices. Okay, so there is some finite number of nodes or vertices in the graph, and in the graph there are some lines connecting these nodes. The lines, they need, whether they are drawn as straight lines or as bent lines or not, does not matter. What matters is that there is a connection. So a connection between these two nodes is what I'm going to call an edge. So there's an edge between some nodes. A graph, in my definition, consists of a finite collection of nodes or vertices and a subset of pairs of nodes. Whenever a pair is there in my collection, it means that the two nodes in that pair are connected by an edge. So those are the edges. And in this, when we draw it pictorially, this is how we draw it. We draw the edges by these lines. The nodes are the circles and the edges are the lines. So this is the definition of a graph. And every network I can model like this as a graph. And when I model a network as a graph, the meaning is that every node is a person in that network, a person or an agent or whatever. If it's a network of computers, then every node is a computer. And an edge, in my example, when I'm talking about people and whether they are friends or no, an edge between two nodes means the corresponding people are friends. Is this definition of a network and as a graph clear? Because this is something that we will repeatedly use in what follows. Okay. So if something is not clear along the way, just immediately speak up and ask me, because otherwise I will merrily go along assuming everything is all fine. Also, if I suddenly start speaking too fast, which I do quite often, please feel free to stop me and tell me to slow down. Yeah. Okay. So we were trying to formalize this question, the connections question, and the connections question is dealing with a network which we are going to model by a graph like this, and yeah, in this graph, A is connected to B exactly when there is a path from A to B. The path is using only the edges of the graph. So in this coloring that I have shown here, for all the pink nodes, there is a path from one pink node to the other. All the pink nodes are connected to each other. All the blue nodes are connected to each other. There is no path from any pink node to any blue node. So that is the connectivity status that we want to find out. And the questions that we are allowed to ask. So this is a small example, but since we are going to be dealing with a huge network where there are millions of nodes, we will ask very pointed questions. Is this login ID person and this login ID person, are they friends of each other? So the questions that we are allowed to ask are, is a particular edge in the graph present? Asking whether X and Y are friends of each other is asking whether the edge between the node X and the node Y is present in the graph. So I'm going to denote it pictorially like this: C to D with a question mark. So that's the question. Is C a friend of D? Okay, so let's look at a very, very small group example. I mean, this is kind of a bit counterintuitive because we are dealing, I keep saying that we are looking at this massive millions of people network, but to get some intuition, let's start small. Just 3 people in the group, A, B, and C. I want to know whether A is connected to B. Okay, so here is one way in which I could go around doing it. The first question we will ask is A a friend of B? Because then they are directly connected. Okay, if yes, then we answer yes, A is connected to B because A is a friend of B. Else, so if the answer to the first question is no, then maybe I will go ahead and ask, is A a friend of C at least? Okay. Now, if the answer to that is also no, then no, B is not a friend of A, C is not a friend of A. How is A going to get any other route to reach B? Because there are only 3 people in this network. So if the answer to the second question is also no, then you can reply no, A is not connected to B. But if the answer to the second question is yes, then what we know is that A is connected to C. Is that enough to conclude that A is connected to B? Well, for that, there must be a connection between B and C. So then I should ask, is B connected to C? Is B a friend of C? And if the answer to that is yes, then we can answer yes. Otherwise, we can answer no. So this looks like a very boring and verbose way of writing so much text. It's much, much simpler to deal with diagrams. Just as that huge network also, I said we will draw it like a graph. So even this procedure to decide whether A is connected to B, we will have a diagram representation like this. So I start at this topmost node here. These blue nodes here are the question mark nodes. So it's this blue oval node here. It is labeled by, is A a friend of B? There are 2 possible outcomes. You may get an answer yes, or you may get an answer no. If you get an answer yes, then you know the answer. You know that A is connected to B, so you say yes and you stop. If it is no, then you look at this thing. You next want to ask, is A a friend of C? And if even for this the answer is no, then you know A is not connected. So you put this. So this no here corresponds to the no in this line. This no here corresponds to the no in the last line. This yes here corresponds to the yes in this line. Okay? So this text description that I have up here on the left can be represented in this diagram on the right. And this kind of diagram, which I've shown here on the right, is what we call a decision tree. Okay. So why a tree? So actually, when you think of it as a tree, in a tree, so this node is considered the root. And these nodes, from where you can't go any further, you already have the answer, are the leaves. So you have to mentally visualize a tree growing upside down. The root is on top and the leaves are coming down. Okay. So starting from the root, you keep going, branching. So these are various branches of the tree. It's producing more and more branches until it finally reaches a leaf, and then the growth stops. Okay. So a tree in computer science looks like this, as opposed to a real life tree. And this is a decision tree because it is allowing us to finally make a decision, yes or no. It is also whether it finally makes a decision or no is not so important. What is more important is that at each node of this tree itself, we are making we are being given a decision. So is A a friend of C? There are 2 answers, yes or no. Okay. This is decided based on whatever is the actual network there. And once you know which way to go, then you start in this tree and you walk down based on the answers that you have got until you reach a leaf. And whatever is the answer written at the leaf is the answer to the question that you're looking at. So that's how we will represent a way of solving this question through a decision tree. So is the model for a decision tree clear now? We'll see a lot more examples of decision trees. So I hope that, like I said, if there is something which is not clear, please stop me immediately. Okay, so now here's a more real life example. How did you decide whether to register for this whole series, STEMS Tessellate? So there are so many factors which go into it. It's not that somebody tells you, hey, there's this series and you immediately sign up. So I've pulled out a few factors. There are so many, but let's just pull out a few of them, and you can put that also into a decision tree. The first thing you will ask is, well, is this interesting? So you read a little bit about a program. If it's not interesting, you're not going to register. Straight away, you go to no. But if you find it interesting, then the next, okay, so then it is interesting. Maybe I should go. Am I free on those dates? Or do I have some other exam coming up or something? If I'm not free, then I'm not going to register. If I am free, then the next factor, okay, is it affordable? There is some registration fee. Can I afford to pay that? If it's not affordable, then forget it. I won't register. It is affordable, then look at this path. The program is interesting. I am free on the dates of the program, and it is affordable to register for the program. Then you go ahead and register. So this is just a thought process which must have gone on in your heads when you were deciding whether to sign up for this or no. I am using this model of a decision tree to represent it, to represent what was that thought process which finally led you to this answer. You are here, so it led you to this answer. For several other people, it led them to this answer, and maybe there are other factors also. I've just drawn a few here. So this is a real life example where a decision tree is modeling the way in which we decide how to proceed with a task. Okay? And there are many real life examples. I mean, this is maybe this seems a bit concocted, but planning, should I buy a ticket for the match, some sports match coming up? Well, there are lots of factors. Is it likely to be an interesting game? Who is playing in this game? Is the ticket too costly? Is it likely to get rained out? In that case, I shouldn't even bother. Am I free on that day at all? No, all these things you can arrange in a decision tree, which will finally tell you whether you should bother to buy a ticket or not. Troubleshooting, we see this all the time. Your computer is not connecting to the internet. What is wrong? Even if you call a call center number, they are going to walk you down through a decision tree. Are you sure this thing is plugged in? Are you sure this app is running? Are you sure that program has got the right permissions, and so on? So it's walking down a decision tree. Another real life example would be medical diagnosis. You could be worrying about, do I really need a COVID-19 test? This is very relevant to our current situation. In fact, I tried to find a decision tree for precisely this question: do I need a test? And it turns out that at least in India, even on the Ministry of Health and Family Welfare side, there is no such decision tree. But there is one site in the US from where I picked up this tree. There are many sites in the US, all over the world, which have decision trees like this. And the reason why I have specifically picked this up is not for the text. You don't need to read all of this. Is just to tell you that when we computer scientists say that something is a tree, it does not look like a tree at all, any more than my previous figures look like a tree. This is a decision tree drawn sideways. My previous decision trees were growing down. The root was up and the leaves were down. Here, the root is on the left. You start off with, are you having symptoms at all? The answer could be yes or no. If the answer is no, then at least this protocol is saying, don't bother, just stay at home. You're fine. If the answer is yes, then you go over to the next question. Are your symptoms severe? The answer could be yes or no. If it is yes, then okay, if you have a doctor, ask the doctor. If you don't have a doctor, then go immediately to the emergency room or the local health center. If the answer is no, they are not severe, but there are mild symptoms, then it's going to ask you, do you have any underlying risk factor? Yes, no. Yes, call your doctor. No, stay at home for 3 days, rest, and then see. So it's really exactly the same kind of situation as in the previous example. It is a decision tree. Like I said, it's just depicted here growing right. And the questions that we are asking at each node are not questions of the form is X a friend of Y. They are different questions. Okay? So what questions you ask along the way are going to depend on the specific application that you're looking at. And you walk through these questions. As you get the answers to each questions, you take different paths in this decision tree until you finally reach a leaf. And at the leaf of this tree, you are told what you should do. Either you are trying to decide some answer and at the leaf there is the answer, or you are trying to figure out how to do a particular task and at the leaf you are told this is how you should do the task. Okay? So this is another example of a real life decision tree. Okay, so what now that we have seen various such examples, maybe we can try to put this together. What exactly is a decision tree? It is a way to specify the decision making process, specify it cleanly and unambiguously so that it's very clear what is going behind this. Okay. What about complexity? So of course, if you want to specify the decision making process, you don't want the process to be very complicated, because complicated processes are difficult to follow through. So what would be the complexity of a decision tree? So the complexity that I am going to look at here is, how many questions do you need to ask before you reach an answer? So here is this first decision tree that we looked at. Is A connected to C in a three people group? The group had just three people, A, B, C, and we want to know whether A is connected to B. And we saw that this decision tree certainly solved the task. This may not be the only one which solves it, but this solves the task. Okay. Now, how many questions do you need to ask to reach an answer? If you are very lucky, one question is enough. You ask the first question, you get the answer yes, and you're done. Okay? So that's the best case. In the best case, one question can give you the answer. At least one question is needed. You don't know the answer without asking any question. Okay? But in the worst case, you may actually have to ask three questions before you can figure out what's going on. Okay? Without three questions, you're not able to do this. That could also happen. So there is a difference between the best case and the worst case. And if you think of this tree, what does this worst case represent in this tree? Starting at the root, you're trying to walk towards a leaf. You don't know which leaf you will reach it. That depends on the answers that you get. But this worst case complexity that I'm talking about here is really saying which is the leaf which is at a maximum distance from the root, very far away from the root. So you have to ask lots and lots of questions to reach it. And the farthest leaf, its distance from the root, is what I'm going to call the complexity of the tree. So we measure the complexity of a tree by the worst case, which is the not which is the farthest leaf, how far is the farthest leaf. Okay. So here there are two leaves which are farthest, this one and this one. And I don't care which one you pick, but basically to reach both of these, you need three questions. So this decision tree that I've drawn here has complexity 3. So that's the complexity of this tree. Now, this tree, like I said, is solving the question, is A connected to B? And this is not the only tree which solves that question. I could have drawn a different tree which starts off by asking, is A connected to C? Nobody says that you must ask that direct connection question first. Okay. So if it's going to ask that, maybe if you ask things in another way, you might get another decision tree solving the same problem, but with a complexity less than 3, maybe a complexity 2. Okay. So what would be the complexity of this tree is 3, but the complexity of the task is the complexity of the best possible tree that you can look at, not the best case in the tree. So you look at all possible trees which are solving this problem. For each one of them, there is the tree complexity. Then you take the tree which has the minimum tree complexity. That is the complexity of the task. So what is the complexity of this task? Figuring out whether A is connected to C, A is connected to B. I'll leave it to you to think about it with a little bit of thought. Not a minute or two, you will be able to see that in fact, no matter what tree you start drawing, you will require three questions on some path or the other. Okay. So let's start small by just looking at the complexity of specific trees and see what we can conclude from there. Okay. So the connections question. Remember the connections question? We have a network which is modeled as a graph. This is the graph. There's a node for each person. There's an edge between nodes who are friends. And A is connected to B if there is a path from A to B in the graph. Questions ask whether specific edges are present in the graph. Suppose my network has n people. Think of n as something very large now. So forget the very small example. N is 1,000, 10,000, 1 million, something like that. So if the number of people is n, how many potential edges are there? Remember, there could be an edge between any pair. There could be an edge between this and this. In this example is not there, but there could be. There could be an edge between this and this. There could be an edge between this and this. So if there are n nodes, how many pairs are there? So I hope you can see this expression. The number of pairs involving the first person is n minus 1 because the first person could be connected to any of the remaining n minus. And then if you don't include the first person, then how many pairs are there including the second person? There are n minus 2. And then including the third person, n minus 3, and so on. So the number of potential edges is this expression, which if you sum up gives you this combinatorial n choose 2, which many of you know already. It is n into n minus 1 by 2. Okay. So it's this large number, okay, the number of potential edges in the network. For instance, just think of this when n is 10. If there's a group with just 10 people, then the number of potential edges is 45. That's not quite a large number, no, compared to the number of nodes. Now, the decision tree complexity of trying to decide whether a particular node A and a particular node B are connected, it's obviously going to grow as n grows. What we want to understand is how does it grow? As n becomes larger and larger, the number of questions you need to ask, you expect that also to become larger. So the decision tree complexity will grow. But how fast does it grow? That's what we are trying to understand. Okay. So let's look at a simpler question. So maybe before we look at a simpler question, I should ask: Are there any questions at this point? Let me give you a minute in case there are any questions. We can look at them now, and otherwise we'll proceed with.
No, I think we'll post it towards the end.
Okay. Okay. So then let's continue. So here is the simpler question that I was talking about. The simpler question. So the earlier question was you had these two nodes A and B, and the question was, is A connected to B? Now I have only one A. There's no B. Okay, this is large network. A is one person there, and I want to know, is A isolated, or does A have at least one friend? So if I assume that the nodes in the network are numbered 1, 2, 3 up to n, and A is the person numbered 1, okay, I want to figure out whether A has at least one friend. I'll first ask, is A a friend of 2? If the answer is yes, okay, I'm done. I know that A is not isolated. Otherwise, then let me ask, is A a friend of 3? Answer is yes, I'm done. I know that A is not isolated. No, keep going down. There are these dots here which may not be so visible. So I'll go down asking one after another until I finally reach this the last person n, and I ask, is A a friend of n? If the answer is yes, again I know A is not isolated. If the answer is no, well, I have asked about everybody. Everybody, they have said no, so then A is isolated. So this is a decision tree which is solving a simpler question: is A isolated? What is the complexity of this tree? A was the person numbered 1, and I asked about, for instance, how many questions do I need to ask to reach this node?
Like it will be an order of n.
Yeah. So in fact, let's look at this exactly. That there are n minus 1, right? I'm asking about 2, 3, 4, and so on up to n. So there are n minus 1 questions that we're asking. So the complexity of this tree is n minus 1. So this tree is solving this task. It's asking n minus 1 questions. Are there any better trees which maybe ask fewer questions by asking them in a different order, juggling them around? What seems likely? If there are n people and you're trying to ask whether A is isolated, should you need to ask n minus 1 questions, or do you think you can do better? So if n minus questions is fine, then this tree is very simple. Okay? Now it turns out that this simple tree is in fact the best possible. You cannot do better than n minus 1. There is no better tree. Right? So this is a theorem. Any decision tree for isolation has complexity at least n minus 1. Okay? Although, like we said, there are n choose 2 edges in the whole network, but a whole lot of those edges are irrelevant for solving this question. Okay? N minus 1 edges matter, and you have to ask all of those. How would you prove that you actually have to ask all of those? So for that, you would use what is called an adversary argument. Suppose there is a decision tree that always asks fewer than n minus 1 questions. Then we can prove that it actually makes a mistake somewhere. In particular, you take this decision tree and you ask, you follow this decision tree on the input where A is actually isolated. Okay? So the A is actually isolated. A is not connected to any of the remaining n minus 1 nodes. This decision tree is not even making n minus 1 questions. So it has not asked about A connected to some other node, let's say some node K. It has not asked, is A connected to K? Okay? And at the end, it has given an answer. So if it has given an answer saying yes, A is isolated, well, it would reach that same leaf even if I put the A to K edge, because it anyway didn't even ask that. And then it would be wrong. On the other hand, if it reached a leaf and said A is not isolated, well, then that is obviously an error, because I started with the graph in which A is isolated. So the adversary argument is telling us that, if you give me a decision tree which is not asking enough questions, I can, looking at the structure of the decision tree, I can figure out an input instance, a network instance on which it is making a mistake. And in this example for isolation, the mistake, it doesn't even matter what the structure of the decision tree is. The mistake is always going to be on either a network where A is isolated or on a network where A has just one friend. On one of these two, it is going to make there are n plus one. There is one network of this type, and these n minus 1 networks. There will be a mistake in one of these. So for isolation, no matter what decision tree you use, the complexity will be n minus 1. Another simple question you could ask is the network in this network, is A universally popular? The exact opposite of isolated. Everybody likes A. You will do pretty much the same thing. You will ask, is A a friend of 2? If the answer is no, then A is not universally popular. Is A a friend of 3? If the answer is no, then A is not popular. Keep going down. If you get all yeses, then you know that A is popular. If you get a no even somewhere along the way, then you know that A is not universally popular. Okay. So if you have seen logical notation before, then the previous one about isolation was asking about an or of some bits. Is at least one of them one? And here we're asking, are all of them one? So the or function and the and function that's what's going on here. So in this case, again, the complexity is n minus 1. And you could ask, is there any better tree? Well, there isn't a better tree. The same argument that we saw informally for checking isolation also works to show that for universal popularity, the complexity is n minus 1. You have to ask those many questions no matter what decision tree you use. Okay? So where is this lower bound n minus 1 coming from? So what is driving the complexity? Let's try and understand that. Whether A is isolated or not, it depends on n minus 1 edges. It depends on the edges from A to 2, A to 3, A to 4, A to n. Those edges which have one endpoint at A and the other endpoint somewhere else. It does not depend on the remaining edges in the network at all, though there are some n into n minus 1 by 2 edges in the network. Because we are not asking about connections. In this question, we are only asking, does A have a direct friend? So it depends on only n minus 1 edges. Okay? But it depends on all of them. Similarly, universally popular or no, that depends on n minus 1 edges. And in both these cases, we saw that the decision tree complexity was n minus 1. So this is a reasonable conjecture to make, that the complexity, the decision tree complexity maybe is the same as the number of edges on which the answer depends. So maybe you should take a minute to think about this. How likely or unlikely is this conjecture? Okay. So I have some question in this network about some nodes, whether they are connected, whether they are friends, or whether they have a common friend. Some question I have, and it depends on some number of edges. And we want to know whether the best possible decision tree must query those many edges. Okay, so maybe it seems reasonable, but it's not obvious, but you want to prove it. Okay, so let's go ahead and see an example. Again, this is a very small example, a very small group, just 3 people. But the question I'm asking is more complicated. Okay, so I have this statement here that somebody has made. Somebody has said A is not universally popular and B is not isolated. So the statement has 2 parts. Both are parts of the statement. Now you want to decide, is this statement true? Is it true that A is not popular and B is not isolated? Now this group itself has only 3 nodes. So there are only 3 edges. Right? Deciding whether this is true, does it depend on all 3 edges or does it depend on only 2 edges? It depends on all 3 edges. Right? To decide whether A is universally popular or no, it depends on whether A is a friend of B. It depends on whether A is a friend of C. To decide whether B is isolated or no, it depends on whether B has an edge to A and whether B has an edge to C. So it depends on 3 edges. So therefore, the decision tree complexity for this, if our previous conjecture, recall our previous conjecture was that complexity is the same as the number of edges on which the answer depends. So this answer depends on 3 edges. So the decision tree complexity should be 3. Here's a decision tree which has complexity 2. I start off by asking, is A a friend of B? If my answer is yes, then I immediately know that B is not isolated. B has a friend. So I don't need to worry about checking the B isolated or no anymore. I just need to check whether A is not universally popular. So I ask, is A a friend of C? If A is also a friend of C, then what has happened? A is universally popular, but a statement said A is not universally popular. So you say false. Whereas if A is not a friend of C, then this tells me that A is not popular. This tells me that B is not isolated. So the statement is true. Similarly, if A is a friend of if A is not a friend of B, I already know that A is not universally popular. So this part of the statement is, the first part is already verified. I really need to verify only the second part. And that depends on whether B and C are connected or not. So I ask this question. If it is yes, then notice how do I reach this leaf? I come along this edge. So I know that A is not popular. And I come along this edge, so I know that B is not isolated. So the statement is true. A is not popular and B is not isolated. Whereas if I come all the way here, I get both no answers, then B is isolated. B is not connected to A, B is not connected to C, B is isolated, so this statement is false. So that previous conjecture, although it looked reasonable, it was not quite correct. Here was a deciding whether this statement is true. So the statement, it has a value which could be true or false. So you can think of that value as a function of your input network, and this function depends on 3 edges, but there is a decision tree which is complexity less than 3. Decision tree complexity was just 2. So we want to understand better if that is not what dictates the complexity, what is, is there something else that we can pull out of this, or can we improve this further? That also we could ask. Complexity is 2, maybe there is another decision tree with complexity 1. Now that is very easy to rule out. Complexity 1 meaning you can only ask one question. You ask one question and then you give the answer. And if you ask only one question, then your answer is not depending on all 3 edges. It's depending on only one edge. And you can very easily find instances where such a decision tree would be wrong. But we want to ask more generally. So what does this 2 here really signify in this setting? So here is what it, in some sense, what it signifies. Let's look at the length of a proof. Okay. So recall the statement we want to prove is statement we want to decide whether it's true or no is decide whether the following is true: A is not totally or universally popular, and B is not isolated. Now I'm going to give you a little bit more work. I'm going to say it's not enough to just say tell me the answer to this. I want to know. I want to see a proof that your answer is correct. Okay. So how are you going to prove this? Well, if you say that the answer to this is true, then you have to prove to me that A is not popular, and you have to prove that B is not isolated. Only then the statement will be true. How will you prove that A is not popular? By showing that someone is not a friend of A. That means you have to show that one of the potential edges is missing. How will you prove that B is not isolated? By showing that B has a friend. So by showing that one potential edge is present. So if your answer to this to deciding whether the statement is true or no is that yes, this statement is true, if that is your answer, to prove it, you will need to tell me about 2 edges. One edge which should be absent, missing, right? Someone is not a friend of A. And one edge which should be present to say that B is not isolated. Okay. Now, there are 3 edges in the network, but telling the status of 2 edges is going to be enough to prove that the statement is true. Similarly, if the statement is false, telling the status of 2 edges is going to be enough to prove it. For instance, this could be false because A is popular, and I can prove that by showing you that both the potential edges touching A are present. Or it could be false because B is isolated, and I can prove that B is isolated by showing that both the potential edges which are touching B are absent. Now that is exactly what this decision tree is doing. Here we reach false, and the 2 questions that are asked along the way, along with their answers, are the proof that the answer is false. On this path, you reach true, and the 2 questions that are asked along the way and their answers is a proof that the answer is true. Now, whenever you reach a leaf, and at the leaf you have an answer, the questions that you have asked along the way to that leaf and the answers to those questions, they give you a proof that the answer is correct. They have to give a proof by the way we have defined decision tree. Because if they don't yet prove this, if there is still something missing, then I can again create 2 different instances which reach the same leaf. And on one of them, the answer is correct, and on one of them, it is wrong. So this requires a little bit of formalization, which I won't do now. But the main takeaway point is that we want to say, if you look at the number of edges that is needed about whom you need to know, are they present or are they absent? The number of edges needed to prove an answer, to prove any answer. Some answers maybe you can prove very quickly with just one question. But if there is even one setting where you need k edges to prove an answer, then the decision tree complexity cannot be less than k. You will have to make k queries along a path before you reach an answer. So the decision tree complexity is at least as large as the length of the shortest proof on any input. So this is why we came down from 3 to 2 in this example, but we cannot go down from 2 to 1 because one edge does not certify anything in this setting. Okay. So far, so good? Okay, so this had the flavor of a bit of toy examples and all. So let us get back to our original question. We wanted to know whether A is connected to B in this huge network. So this is this huge network which has n nodes. including A and B, and there are n into n minus 1 by 2, some n square by 2 roughly edges, and we want to figure out what questions to ask in what order to ask, so that you minimize the number of questions asked and you still figure out this connection question. So in this case, again, the answer depends on all potential edges. Okay. Now this also needs proof, but I'm not going to prove it here. I'm going to leave it to you to think about it. Every potential edge in the network, that potential, I keep saying potential edge because it may be present, it may be absent, but every pair XY could have a bearing on whether or not A and B are connected. Yeah? So all the edges are important in some network or the other. They may not be important in the same network. There is one network in which the XY edge is important. There is another network in which the YW edge is important, and so on. Okay? I mean, when I say they are important, meaning they are make or break. They will decide the answer whether A is connected to B or no. So it's like saying that there is some setting where this edge is the kingmaker. We have been hearing a lot about election data, so maybe kingmakers are on our minds, and that's what it is. Just give me, my phone is. Yeah. Okay. So the answer does depend on a whole lot of edges, but we don't think that a decision tree will actually have to ask so many questions. So how can we pin that down? So we know that the decision complexity tree complexity at most n choose 2 you can ask about every possible edge, but can you do better? If you can do better, how much better can you do? So take a minute to think about what your guess would be and note it down, and then we'll go ahead and see what we can prove. Okay. So remember that the number of edges roughly is quadratic in the number of nodes, right? N square by 2 or n into n minus 1 by 2. So it turns out that the number of edges you need to check is quite large. In a group of 20 students, if I want to check whether student number 1 and student number 2 are connected, it's going to need 100 probes, maybe even more. I'm not saying that 100 is enough. I'm saying you will need to probe at least 100. But how many edges are there to probe in a group of 20 students? It's 20 into 19 by 2, so there are 190 edges, and out of the 190, at least 100 you have to probe, more than half. In a group of 50 students, you have to check at least 625. So these numbers are carefully chosen. From this, you should be able to figure out what the pattern is. The pattern is, for testing connections in a network of size n, any decision tree must probe at least n square by 4 edges. And this is more than half the number of edges, because the number of edges is actually less than n square by 2. It is n into n minus 1 by 2. Okay? So I just want to know whether these two students are connected. This is huge network. When you think of the web, when you think of the Facebook web or the Instagram web, for instance, there are like millions of. But to figure out this connection between two souls somewhere in this huge net, worst case, you have to query half the connections in the humongous network. I'm saying that you have to query half, but we need to convince ourselves that this is really necessary. How would you prove such a thing? So one way to prove it, like we saw, in that previous small example, would be to say that there is the length of the proof is so much. If the length of the proof is so much, then yes, if you cannot prove that they are connected or that they are not connected without using so many edges, then the decision tree complexity will have to be so large. So let's see what is the length of a proof. If I want to prove that A is connected to B, then I just need to report a path between A and B. Maybe A and B, there's a direct edge, a path of length 1, or there is an A to C and C to B, a path of length 2, or A to C to D to B. Worst case, the path could go through all the nodes in that entire network and then reach B. Even then, it's going to have only n minus 1 edges. N nodes you arrange in a path, you have n minus 1 edges. Nowhere near n square by 4. Okay. So to prove that A is connected to B, I just need to report a path which is not too large. But if I want to prove that A is not connected to B, then this is a harder problem. How do I show that there is no connection between A and B? Again, think back to our first very simple example. We kind of split the network into two colors, pink and blue. And there was no connection between pink and blue. So if A was sitting in the pink set and B was sitting in the blue set, and there is no connection between pink and blue, then that's a proof that they are not connected. But then to give that proof, you will have to show that all the edges between pink and blue are missing, right? So how would you prove that A is not connected to B? You would report what I'm calling an insular group. And an insular group is like very inward looking. It's like completely unbothered about the communities outside. It's a small group. Well, okay, not necessarily small. It's a group. I'm calling this group S. It contains A, but it does not contain B. And there is nobody in this group who is a friend with even one person outside the group. That's what I mean by insular. Not a nice thing to be, but yeah, there are insular groups. Definitely on the social networks, right? So if I want to show that A is not connected to B, this is one way in which I could prove it. I would report an insular group which contains A, which does not contain B. But if you report a group, I mean, how do I know that the group is insular? To prove that S is insular, you will need to check all potential edges which have one end in S and one end outside S. And you would need to check that all these potential edges are actually missing in the network, which is why this group is insular. Okay. So if the alleged insular group has size K, then you will need to check how many edges? K into N minus K. There are K edges here and there are N minus K edges outside the group, and all possible cross connections should be missing. Right? So K into N minus K edges would need to be proved. Suppose K looks like N by 2 plus M. Maybe it is N by 2 minus M, but for now let's look at N by 2 plus M. Then the number of edges I need to check is going to be N by 2 minus M into N by 2 plus M. Right? N by 2 minus M is the N minus K, N by 2 plus M is the K. That's why I said that, if K is less than N by 2, it's N by 2 minus M, then, the order of these two factors gets interchanged, but it's still this N by 2 minus M into N by 2 plus M. That's N square by 4 minus M square. And that's strictly less than N square. That's no more than N square by 4. You're taking N square by 4 and if at all you're subtracting something from it. For those who had seen these kind of graphs before, you can see that what we're saying here is that N square by 4 is the size of the largest cut in the graph. You cannot have a cut which is larger than this. And the cut is exactly, the insular group is the edges which are missing going out of the insular group are what are forming the cut. Okay, so yeah, an insular group could have N square by 4 edges missing going out of it. In particular, when do you actually reach N square by 4? When K is N by 2, right? So let's look at a network which is like this. I have half the nodes here inside this circle and A is there in this. I have the other half nodes in this circle. B is there in this. And now imagine that your network looks like this. Within this circle on the left, all possible connections are there. Everybody is a friend of everybody else. Similarly, imagine that in this circle on the right, everybody is a friend of everybody else. Okay? So lots of edges are present in the network. But what about edges which go across? I'm not telling you right now whether they are there or not. So if none of the edges which go across are there, then it means that this is an insular group which contains A and which does not contain B. And so A and B are not connected. If there is even one edge from this set to this set, I mean, it need not be from A to B. It could be from this node to this node, or it could be from this node to this node, or it could be from this node to this node. If there is even one edge from the left circle to the right circle, then immediately I know that A and B are connected. Why? Because from A, I could go to that node, which is connected to the right. Then I hop across on the right, and then from there I go to B. Remember, within each circle, all edges are present. All connections are there. So if there is even one of these edges which is present, then A and B are connected. And if none of them are present, then A and B are not connected because we have the insular group. So now with this, now you can go back and think about one of the earlier decision trees that we drew. We want to decide, is A connected to B? In this network, what that decision tree would have to do would be check all these potential edges. If even one of them is present, then the answer is yes. Right? So it has to check each and every one of them. Without check, if it misses out any one of them and it says that yes, A and B are not connected. So let me start with the graph where actually A and B are not connected. Okay? All these edges are absent. So I know already that A and B are not connected. The decision tree does not know it because the decision tree does not know what network it's going to get. And it's on this graph where which does not have any of these middle edges, it follows some path. I'm claiming that that path must check each and every potential edge in going from left to right. If it misses even one edge, then it's going to reach the same leaf on this graph as well as on the graph with that one missing edge. So on both of them, it's going to give the same answer. But the answers on these two graphs are different, right? In one case, the answer is yes, in one case, the answer is no. So we're just using the fact that if on two networks the answers are different, then the decision tree should take them to two different leaves. It cannot take them to the same leaf, because at one leaf there is only one answer. So this is an argument for why you actually will need to probe at least n square by 4 edges in order to decide whether A is connected to B. So you can see about a thankless job it is to figure out disconnections. We keep hearing in that the distance of connectivity on the social network, 6 degree 6 distance 6, everybody is connected to somebody else within distance 6. That may be the case, but how are you going to figure it out? You have to ask the millions of questions before you will even find such a path. Okay, so this was about proving A is not connected and to B, and therefore saying that the decision tree complexity for connectivity is quite large. It's at least n square by 4. I'm still not saying that it is exactly n square by 4. It may be more than that, but it's at least this much. Okay. I could ask another question, which is even more than this: total connectivity. Instead of asking is A connected to B, I ask is A connected to everybody in the network. Well, actually, the way I've written it here, I've asked decide whether everyone is connected to everyone else. But I think you can quickly convince yourself that this is equivalent to asking is A connected to everyone else. Is that okay? If A is connected to everyone else, then you take any pair anywhere in the network. From there, X, Y. From X, you can go to A, and from A, you can go back to Y. So you can go from X to Y. And if A is not connected to everybody else, maybe A is not connected to some X, then everyone is not connected to everyone, because A and X are showing that this is not the case. So although I've said this is total connectivity, everyone connected to everyone else, you could pick one node A and ask, is A connected to everyone else? That's the question you want to answer. Again, you could ask, does this depend on all the edges? Yes, it does. But what is the decision tree complexity? It turns out that for this question, I can actually show that the decision tree complexity is full. You have to probe each and every potential edge. Recall in the previous case, I only said that the complexity is n square by 4. It's more than half the potential edges, but it is not equal to the number of potential edges. It's less. Okay. So that was when I was only figuring point-to-point connectivity. For total connectivity, there is no gap at all. We can show that every decision tree solving total connectivity, it must have at least one path that checks every potential edge. And I don't want to give a full proof of this, but maybe we can just think online at this stage about how would such an argument go. You would, given a decision tree which is trying to solve this connectivity problem, I'm going to think of myself as an adversary. I'm going to show, let's say that you have the decision tree which solves total connectivity, and maybe you are claiming that it has complexity less than n choose 2. It's not looking at all the edges. It's not looking at all the edges. And I am the adversary. So I'm going to produce a graph on which you are forced to look at all the edges. So how will I produce the graph? Well, one way would be to look at your decision tree and then produce it. But instead, I will do it one step at a time. Initially, I have all possible graphs. Now you are the decision tree. You want to walk down the decision tree that you have. So you ask me the first question. And then I give an answer to that. And that's going to restrict the number of graphs that I have present with me. And then you ask the next question. So I have not fixed in mind a particular graph with respect to which I am answering. I am keeping a pool of graphs, but all the graphs that I have are consistent with the answers that I have given so far. So I will gradually narrow this pool down until it comes to and I will gradually narrow this pool down and force you to ask more and more questions before you are able to reach an answer. So there is an adversary argument which figures out how to shrink this pool of graphs, and all the edges will have to be probed before an answer can be given. Okay. So I don't want to go into the formal details of this proof, but it's a very interesting exercise. So I would suggest that if you found it interesting so far, try to figure it out yourself. I mean, I can always give a reference and say read it up here, and you can read it in 5-10 minutes and know what's going on. But really, try to figure out yourself, why is it that every edge would have to be read? How could you force a decision tree to read every edge? It's a very nice exercise. So I would suggest that you try and do that. Okay, so just a quick wrap up. I think we are almost at the end of our time. Why do we study decision trees? So I have looked at decision trees for very specific questions so far, right? The connectivity question, isolation, popularity, connection between A and B, connection between A and everybody else. These are all connectivity questions. But you could look at decision trees for all kinds of tasks. We saw various examples before. And the reason why we look at decision trees is because they help us to understand many things. I gave real life examples at some point along the way, but even at a more mathematically abstract level, studying decision tree complexity helps us to understand, for instance, what functions are easy to compute, what functions are hard to compute. And when I say easy to compute, hard to compute, I don't mean easy to compute in a decision tree. I mean easy to compute by computers, by circuits, by the most general model of computation that you could think of. Trying to understand hardness of computation, decision tree complexity does play a nice role there. Similarly, it helps us to understand what kind of statements are hard to prove. So maybe a statement is true, but to write down a formal proof of it is very hard. And there are some very nice connections between decision tree complexity of a function and a statement related to that function and writing down a proof of that statement. There are also connections between decision tree complexity. In fact, these are the most prominent connections between decision tree complexity and what is called communication complexity. So, there are joint projects between partners sitting in different, and right now we are all sitting in different cities, and we need to communicate, and maybe communication is costly. So the question is, what kinds of collaborations require a lot of communication? What are the collaborative tasks that are very hard from the point of view of communication? We would like to understand this better, and decision tree complexity helps us to understand that. So here, these are many different ways in which decision trees pop up in a more mathematical setting. In a real life setting, of course, like I said, there are examples a dime a dozen, and I would encourage you to go and look up. So do you want to know more about this, or perhaps you are not sure whether you want to know more about this? In that case, you should be thinking about what are the factors that will help you. You should plot a decision tree which will help you to decide this. Yeah. Okay. So with that, let me stop now, and I hope you enjoyed this, and I'm open to taking questions.
Ma'am, so as you said that for deciding whether A is a friend of B, or like A is connected to B or not, we need at least n square by 4 edges. So you mentioned a lot of times that there can be like millions of like cases. So like at that case, like n square will be too much high. So like how do actually computers like do they find like some other method to also like sort like take out the possibilities out of n square by 4?
Okay. So what we're asking is that we know that the decision tree complexity is too large. So the real computers cannot actually be doing that. What are they really doing? Because they are solving this problem all the time. So the decision tree complexity can be very large, but an algorithm which would be written to solve this problem is not necessarily a decision tree. Right? A decision tree is one particular way of representing the method in which you could find the answer. So that is one way to think about it, that this is not the only possible algorithm. But on the other hand, if you think about a generic algorithm, so a generic algorithm is allowed to ask, it's still asking the same questions. Is X connected to Y? It's like X connected to Y is asking for a bit from the adjacency matrix. If you had to, if you have just started coding and you were to write a program to figure out whether A is connected to B, the first thing that would come to mind would be, maybe you should do a breadth first search or a depth first search.
Yeah.
Right?
Yeah.
And you say, okay, these are very efficient. How efficient is depth first search?
Linear, it is V plus C.
Linear. So what is linear? Number of nodes plus number of edges.
Number of edges.
Number of edges is n square.
Yeah.
Right?
Yeah.
So even those algorithms which we think of as being very efficient are doing this n square by 4, but they are doing it in the worst case. So what is saving us in practice is that in many cases you very quickly find an answer.
Yeah.
Okay. So remember, in all this I was looking at the worst case complexity, but maybe for most inputs you find the answer very fast, and there are occasional inputs on which you require a long time. The way we have set up our notions of efficiency, we still consider n square to be efficient because it's polynomial in the size of the input. But
Yeah.
it's true, it is not really. So massive data requires a different way of handling as compared to normal uh, data that we can store in one place.
Oh, yeah. Thank you.
Maybe I should stop sharing so that I can see faces.
I had a question.
Yeah.
Ma'am, is there some way to do this process statistically? That is, I don't want all the answers to be correct. I want more or less 90 to 95% answers to be correct. But that reduces the number of things that I have to check by a drastic amount. That is, the order changes from, say, 2 to 1 something. Is there a way?
Yes, there is a way. So this is a very nice direction that you are mentioning, which has been studied quite a bit. So there are what are called randomized decision trees. Okay, so at each point you ask a question and you could get an answer yes or no, and accordingly you go left or right in the tree. Alternately, at each point you could also flip a coin and randomly decide, should I go left or should I go right? Okay, so you don't have enough information about where to go, but you just randomly decide where to go. And then what is the behavior that you would expect? You would expect that, so this, now if I construct a randomized decision tree like this on the same input, on the same network, if I run it today, it leads me to one leaf with a particular answer, and I run it tomorrow and I flip coins, I may get a different sequence and I end up in a completely different leaf, right? And the answer could also be different. So on the same network, this randomized decision tree is possibly giving me different answers based on the outcomes of my random coin flips. What I would demand is that it should it can give different answers, but with very high probability it should give the correct answer. Now the formalizing this is important. I could formalize it in two different ways. The way you asked was, for most inputs it should give the correct answer. Now that is not a randomized decision tree. That would be, you have a deterministic decision tree, which on some inputs it makes a mistake, but on most inputs it gives the correct answer. And the way I am saying is that I have a randomized decision tree. On every input, most of the time it gives the correct answer. Now these two notions are related. They are related, and the moment you bring in this kind of randomization, which says that okay, with I'm willing to accept a small error probability, the decision complexity comes down drastically. It does. Yeah. So there is a lot of information about randomized decision trees that you can get connected to randomized communication complexity also.
Thank you so much, ma'am.
Ma'am, there is another question. So the question says that is there any way to prioritize some few connections which can lead us to quick answer? Like
That
maybe
is
we can, yeah.
that is I think what your first question also was asking about, how do algorithms work in practice so fast. They do some prioritization, so especially when they find nodes with very high degree connected to lots of people, then first go and check those because they may very quickly lead you to these connections. So the
Right.
page rank, I don't know, some of you may have heard of this
Yeah.
called page rank, trying to figure out which are the most popular pages which point to many other pages which are pointed to by other pages which are also very popular, and then you focus on those first. There are of course outliers which have very few connections, but the chances that you have hit an outlier are so small that you deal with those later only if you have to. So this would again be a kind of average case analysis, that if you focus on the high connectivity part, then on an average you will end up doing things better than in the worst case.
Right. Yeah. So like in average cases, like the algorithm works pretty fast. Then.
Yes.
Yeah. Thank you.
So my question was, in reality, like the websites only have to run this, like they won't have to run it every single time for a user, right? So they can actually store the connected components, and then when a new user comes, we might like uh, uh, compare the user to every existing person. So that would take linear time for each individual person.
No, so where would
And
you store this?
maybe on a database
So
or something.
the running example that I keep giving is Facebook.
Okay.
So I don't think there would be one storage site somewhere which has data on all the Facebook users.
All right.
That every time a new user joins, the thing is added there. Every time a friend request is made, is accepted, it is updated at one side. That will not happen. The information is also
Okay.
distributed, right? And the information
Okay.
is huge. So the information is so
Okay.
huge that in fact you will not be able to store it all efficiently in one place anyway.
Yeah, yeah.
So
And
that is
one
what is
more
causing.
question.
Also,
So,
actually, maybe I should also say that even if you had enough storage capability at one place, when one
hmm,
person joins in, I I don't think that one person would consider it acceptable having to wait for time which is roughly n. See, we are talking about n and n square. Oh, n square is too big, we can't do with n square. N is, but even n. I mean, in this realm of massive data where there are millions of users, if you have to wait for million things to be updated just because you are doing one little thing, you're not going to be happy. So when you're talking about massive data,
yeah.
what is acceptable is going to be not something like order n, but order log n, and that you
Hmm.
cannot do by the method that you described, where
Okay. So
update
there'll be
decentralized
sublinear
information.
algorithms, right?
You will need, yeah, sublinear, severely sublinear.
Okay. Thank you, ma'am.
I can see one raised hand somewhere, but no.
Yes, ma'am. That question is answered.
Okay, that was okay. So I'm not sure of the background and the level of people who are here, which is why I did not put up an explicit reference. So for college going students, I would say that if you are interested in looking at more about decision trees, then a book on complexity theory would probably have a chapter or half a chapter on this, which would be nice. At high school level, I'm not very sure what material I can even suggest. So that's why I did not put it up here.
So, ma'am, there is another question. Is there a sort of any open problem or very hard problem regarding related to decision trees, which we can understand, like people can understand this stage?
So so the hard problems that the open problems that I know of are of the type which I mentioned on the last slide, which was you use decision tree complexity to understand other things. Okay, so for instance, there is this setting where, let's say, f is a function which looks at some n bits and then says gives a value which is either 0 or 1. If I can show that f has high decision tree complexity, then a, a slightly shifted version of f composed with some other function g, which is usually called a gadget function, is going to be hard for communication complexity. Okay, so these are the kind of results which are so in decision tree complexity, it is relatively easy to show that something is hard. Almost all things are hard in decision tree complexity, and it's relatively easy to show them. But tight bounds, I mentioned, for instance, that the decision tree complexity is at least as large as the length of the length of a proof on any instance, and that is what is called certificate complexity. Okay, so we know that the decision tree complexity is at least as large as the certificate complexity. What about on the other side, upper bound? We know that it is at most as large as the square of the certificate complexity. So it lies between certificate complexity and square of certificate complexity. At both ends, these bounds are tight. There is a function for which decision tree complexity and certificate complexity are the same. There is another function for which decision tree complexity and certificate complexity square are the same. But what are the tightest possible factors that you can get between these two? That's, function by function, people are still trying this out. And the reason why we are trying this out is that we want to get the maximum number of gadgets, maybe smallest gadgets, for which we can then lift this and then say something about communication complexity. So certainly the open questions in communication complexity are being tackled by looking at questions in decision tree complexity.
Okay. Okay.
Does that answer the question to some extent?
Yes. Yes. That
Yeah.
means.
Okay.
Ma'am,
Yeah.
ma'am, I had another question that rather than asking a simple yes/no question, can we ask something else?
Oh,
Like
yes.
how many people is he connected to get a better clue or to have less number of questions?
Yeah. So that in fact would be another answer to the previous question, that what are the other kinds of open questions that you could ask. So people have looked at models where, so what I described was a simple decision tree. Then there are things which are called, for instance, an OR decision tree. At every node, instead of asking about one edge, you specify a bunch of edges and say, is at least one of these edges present? Okay, that's an OR decision tree. So if even one of them is present, then you will go to the yes side, otherwise you will go to the no side. You could have an AND decision tree. You could have a parity decision tree. You specify a bunch of edges or a bunch of bits at a node, and if an odd number of them are on, then you go to yes. If an even number are on, you go to no. You can even go further. Why just have two answers? So you can specify a bunch of edges at a node and say, this is the bunch of edges I am interested in. How many of them are actually present? 0, 1, 2, 3. So if the set I have specified is of size k, then 0, 1, 2 up to k, there are k plus 1 possible answers. But if k can be arbitrarily large, then you get too much information out of this. So one model that people have looked at, which comes up also from learning theory applications, is that your set can be arbitrarily large, the set of edges that you are querying at a node, but the answers you are allowed to answer, none of these edges are there, exactly one edge is there, exactly two edges are there, more than two. No, so there is some cutoff. The set may be of size 100, but I am only distinguishing between 0, 1, 2 and more than 2, or 0, 1, 2, 3 and more than 3. Okay, so you create trees like this where with each question you get more than two answers. And normally when we think of non-binary trees, you can convert to binary trees with a little bit of blow up, but it does not quite happen this way in this setting, because if there is exactly one edge which is present, you don't know which one it is unless you query all of them. So it's not that you are going to blow it up just by a tiny amount, by log 4 or something. It could, the decision tree complexity could go up hugely. So this model will suddenly change the complexity quite significantly. So this model is what is called k plus decision trees, 0, 1, 2, 3 or more than k. And k plus, in fact, some recent research work that I remember having seen maybe 5-6 years ago looks at randomized k plus decision trees, and has some very nice results connecting it to other notions of complexity. So certainly people have looked at many different kinds of decision trees. It doesn't have to be just yes no, it doesn't have to be querying just a single bit at each node.
Thank you so much, ma'am. Ma'am, just one more question. Is it physically possible to actually ask the questions? That is, I'm saying that let's say we have some user who is using something. Can the internet ask it directly that how many people are you connected to? Or does it have to check each edge to know that all in the first place?
That would depend on I don't know, on the model and the application. So if you are looking at friends, for instance, you are looking at the friend status between two nodes, right? Is so and so, is B following A?
Ma'am,
If you have access to that, or if you can directly go to this person's page and see how many followers are there, that is telling you how many friends. But these are directional edges. Right? A follows B does not mean B follows A. So you could, if this information is publicly available, you can just directly go and look it up there without the number at least, right? So it would depend on the specific application.
Thank you, ma'am.
Ma'am, there is another question, a bit general question. Like, are there any good references to start this from a non-computer science background, like people who are in physics background?
Okay.
And does it have any implication in fundamental sciences?
Oh, does it have any implication in fundamental sciences? Yes. I mean, to me, communication complexity and information complexity are totally fundamental. And like I said, decision tree complexity is helping us to understand that better. But yeah, in terms of a reading reference, I should have prepared. I mean, I cannot think offhand of something which is not computer science. So that's if I think of something later, maybe I will post a comment on the.
As a beginner level, it will work.
Yeah, because I mean, I have seen stuff like this in the complexity theory books, and so that is not really beginner. But if you have some computer science background, you can directly jump to those chapters and read them, and it is readable. It uses a lot of math notation, maybe. So, for instance, there is this, it's a complexity theory book by Stasis Jukna called Boolean Function Complexity. It has a chapter called Decision Trees. And that is maybe chapter 14 or 15 in the book. But you can directly start with that chapter and still get a fairly good sense of what is going on. But if you are not coming from computer science at all, I mean, right now I can't think offhand of what I would recommend as a beginner text. So, like I said, if I do think of something, I will post a comment later on the YouTube channel.
Okay, sure, ma'am.
Yeah, I'll do that. Yeah, maybe we don't have enough popular literature about this to point people to.
So if so there yes, so like there are like comments. So like in so someone has developed some theories regarding fundamental physics using graph theory arguments. So that erases the question that
Oh,
whether
I see.
this is tricky.
Okay, okay. But then the well, in the decision tree, the assumption is that the question being asked at every node is something which is easy to answer. So if you put in very hard fundamental questions in the nodes of the decision tree, then it is not going to take us forward much. It may give a more compact representation of a hard problem. I don't know whether it will.
Yeah, that makes sense.
Yeah.
So okay. So if there are no other questions, then maybe we will conclude this. So if you have any other questions after that, then you can post this. Mail us to at tesla.cm. And uh, sorry, Anudhan, can you continue?
Take care of it. Yeah. So yeah. So if you have any other questions, do post it to us at tesla.cm@gmail.com. I'm posting the link in the chat box. So firstly, before that, thank you very much, Professor Meena, for this wonderfully structured talk. Must have been it's really interesting. So thank you very much for that. So so stay updated about the future talks which STEMS is conducting. So we have one on the 14th of November by Professor Amarjit Budhiraja by the University of North Carolina, Chapel Hill, where he'll be talking about the world of probability, a gentle introduction to it. So starting from how probability even began its roots, starting from casinos and gambling, going all the way to coin flipping, dice, and everywhere, and going all the way to the probability we have now. So he'll be giving a very gentle introduction to the world of probability. So see you all there. And thank you very much, Professor Meena. And thank you, everyone, for joining. I hope all of you enjoyed and will continue to enjoy also.
Thank you, ma'am.
Thank you, ma'am.